Thank you, people from SCS VMV who have joined. Good.
So Kishore, how is the distribution? Like, do we have time for question answering at the end or something like that?
Sir, we will have the after the session. We'll have some Slido quiz of 10 questions that you have given to like an quiz competition. We'll have for 10 minutes, and after that Q&A session, then vote of thanks. Sir.
Okay, so I need to stop by what time? 3:20 or something?
3:15.
3:15. Okay.
Why has Nirmala Krishnan raised her hand? Can you put something on the chat? Or if it happened by accident, just lower your hand.
You can see my video, right?
Yes,
It's a bit blurred,
your
but
face.
though,
Yes,
yeah.
yes.
Okay.
Yeah.
Okay.
Let's
Nice.
restrict the chat box usage to host and co-host.
Can we start, madam?
Yeah.
Okay, sir. Lavana, madam, can you record? Thank you. Welcome to the PALS Industry Astral Lecture online lecture series on generative AI masterclass from LLMs to agents and knowledge grounded system. I am Kishore from PALS Program Management Office. I will be moderating this session today. This is a 4-part lecture series. We'll have 4 lectures. I have listed the 4 lectures and the speakers details and the dates on the screen. I have also shared through mail. You can log in the same meeting ID for the 4 lectures and same timing, 1:30 to 3:30. It's the timing, fixed timing. Today is the first session by Dr. Vishwajit. And I will give basic PMO instructions that to be followed. For easy identification, please rename your Zoom display name as college short name and your name. Participants will stay muted and allowed to unmute only during the Q&A session. Chat box usage will be restricted. You can message the co-host or host. We will enable it only on need basis. During this session, if you have any questions to be asked to the speaker, please write to askpalspmo@gmail.com. This mail will be monitored throughout the session. Ensure to write your name and college short name along with the questions. The other way to ask your question is use raise hand option to interact with the speaker. Attendance link will be pasted in the chat box. Please use the registered mail ID to mark the attendance. Participants are requested to log into the Slido in the beginning of the session. Now I request Mr. Pati Lakshminarayanan, PALS champion, to give the opening remarks and introduce the speaker.
Good afternoon. Thanks, Kishore. Good afternoon to everyone. How many of you have used any of the ChatGPT to finish an assignment or debug or even to just create a birthday wishes for your loved ones? Have you used?
Yeah, we can raise.
Today, it has come as a integral part of any of our life. And then if anything is there, we want to go to some LLM model or generative AI like OpenGI, like ChatGPT, etc. So we are going to know more about this LLM models today with help of IBM Research India Foundation, who are our industry partner for all. It is wonderful to see many bright engineering students from our partner institute PALS here today, and then the registration for this course with the shortest duration of availability because we just started last week to introduce is amazing. That shows the importance of this topic as well as IBM amongst the colleges. Thanks for all of you who joined. Definitely, I will say that you are going to have a lot of benefit by attending all 4 classes what we are having, or 4 sessions you are going to have it. Over the next few sessions, you will be exploring what generative AI really is and how large language model is like Granite are built and trained. Hands-on practice with IBM Granite model, how to design smart prompts to get best results. Agentic AI, which is the topic of the industry today. Every industry talks about agentic AI. So what is agentic AI? Where AI system can think, plan, and act like assistants that go beyond just answering the question. That will be talked in the 3rd session. And finally, knowledge grounded AI through RAG, retrieval augmented generation, which is a relatively new topic in the industry, but it is getting a lot of prominence. That will be taken in the last session. This is just not a theory. You will get try things out of your laptops, ask questions, and work with ideas that are at the cutting edge of the technology today. Remember, my dear students, you are building the foundation for your future careers. The concept you learn here can spark ideas for projects, internship, and even startup for you in future. So please take it very seriously, put your effort, and then this is your chance to learn directly from IBM research stalwarts who are involving and who are solving global challenges with AI today. With that, let us get started. Please join me in welcoming our speaker for today, Dr. Viswajit Kumar, research scientist, IBM Research India. Dr. Viswajit Kumar is a staff research scientist at IBM Research Lab. He works on interesting novel problems in the areas of natural language processing, machine language with current focus on large language model for retrieval augmented generation, RAG also. He has published more than 30 research papers in reputed ML, AI, and NLP conferences like ACL, EM, NLP, NAACL, PAKDD, ISWC, SAGR, etc. And he owns more than 15 plus intellectual patents. Thank you, Viswajit Kumar, for joining today with us. Over to you.
Thank you, sir, for the kind introduction. Okay, let me get started. Can you see my screen? Yes, no?
Yes. 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 On. Not able to see.
Yeah.
Screen is stopped.
Not
Can you
gone.
reshare, please?
Okay. I'll try to reshare. Share entire screen. Okay.
Alt tab.
Wait.
Right. It's going off.
Yeah, just give me a second. Maybe the monitor is. Okay. Now you can see my screen, right? And hear me
Yes.
clearly?
Yes.
Okay.
Yes.
Okay. Hi, everyone. Let's get started. So today I'm going to talk about the very basics of all those technologies which I think Sir talked about, right? Chat GPT, Meta AI, and lot of things have come up, right? Perplexity AI, and so on, right? So everything is based on large language models, right? So today, let's dive deeper into what a large language model is, how it is built, how it is trained, how it is fine tuned, and how we can use it for our own applications. Okay. So I have a detailed deck of slides, but I'll be skipping some of the content, some of the detailed content because we don't have that much time. But yeah, feel free to ask queries or anything, any doubts you have in the middle. Okay, let's get started. So I will be covering introduction of LLMs, and I'll be covering IBM Granite family of LLM models. I'll cover some basics of transformers, pre-training, and fine-tuning, and then I'll tell you about some new models coming up from IBM and some applications and so on. Okay. So what is a large language model, right? So you can think of it like a neural network which takes a context or prefix as input and gives you a distribution over possible set of tokens or the words, right? So given so long and thanks for as input, it attempts to predict a distribution over vocabulary where you get the highest probability for the next token, right? So you get the highest probability for the token all, right? Or the word all. For all other things, you get a relatively lower probability, right? So it is just projecting your representation into a vocabulary space, right? So it is just learning to predict the next token, next possible token, right? Okay. So LLMs can learn to generate. It can keep on generating tokens, right? So long and thanks for all. Then it can generate the and so on and so forth. It can keep on generating, right? That's why the term generative AI, right? It can keep on generating tokens one after the other, right? Okay. So this is basically an LLM, right? Large language model, which when pre-trained, it can generate tokens given the prefix or the prompt, right? When you say like who is the president of US, current president of US, it gives you an output, right? Which is the next set of generated tokens, right? And you have a control at the end, right? Like stop generating when you reach in end of sentence token, or stop generating when you have already generated some, say 128 new tokens or something like that, right? Okay. So there are basically three architectures of large language models which are prevalent. The first one is decoder only models, decoders. The second one is encoders, which are used for embedding models and text representations, sentiment analysis, classification, and so on and so forth, right? And there are encoder decoder models which are used for machine translation and speech to text and so on, all the sequence to sequence applications, right? So all these LLMs like GPT, Cloud, Llama, Mixtral, Granite are examples of decoder-only models, right? Where the goal is to predict the next token given the context, right? Okay. Next is encoder-only models where you attempt to get a representation of the whole token, right? And suppose the first token is CLS token, then that token can have the representation of the whole sequence, right? Compressed representation of the whole sequence. Okay. So I'll be going through details of all of these architectures along with their basic building block, which is transformer architecture, right? Before that, let's dive into LLM categorization. Let's try to categorize LLMs, right? So LLMs can be small language model, less than 1 billion parameters. It can be medium language model, 1 billion to 10 billion parameters. It can be large or very large language model, depending on the size. If it is like 10 billion to 100 billion parameter, then it is a large language model. If the parameter size is 100 more than 100 billion parameters, right, then it is a very large language model like GPT-4, GPT-4o and others, right, which have around 175 billion parameter model. So this is categorization in the space of parameters. Then it could be based on originality, right? If it is just pre-trained language model, then it is called as an original or foundation model, right? So like Llama GPT-4 is an example of original models, right? Which are not fine-tuned for any specific task. Whereas Alpaca is a fine-tuned model, which is fine-tuned on task-specific data, right? Based on Llama. Then there is categorization based on availability, right? If the model weights are publicly available, then we say that this particular model is a public model because the weights, parameter weights are available in public, right? So recently GPT OpenAI has released GPT OSS weights, right? So it became a public model. Then there are private models like GPT 4o, for which weights are not available, right, online publicly. So this is a private model. Then there are types based on types, categorization based on types, right? Like chat model, instruction model, and foundation model. So when you just pre-train the model without doing any instruction tuning or chat specific tuning, then it is called as foundation model. When you tune the model, pre-trained model on instructions, task specific instructions like summarize this text or answer the query based on the content, or you say like translate this text into English or French or Tamil, Telugu, Malayalam, something like that. Then those models are called instruction tuned model, which are tuned based on instructions for specific tasks. Then there are chat models, which are tuned on multiple conversations, right? Like you have chatbots, right? Chat GPT is also one of the examples of chatbot, which has been tuned on multiple chat.
Yes, sir.
Recording stop or something?
No, sir, your screen stopped, sir. When you reach
Your
your
screen
end.
has
Oh, I don't know what
Kind
is
of
happening.
frozen, so we all made it no video, so then maybe
Oh,
bandwidth issue.
okay. I'll stop the video then. Yeah, you can see my screen now. Yes.
Yes.
Okay.
yes,
I was here at LLM categorization.
Yeah.
Okay, you can see my screen with LLM categorization slide, right?
yes,
Yes.
yes,
Yes.
Okay. Okay. Let's move on. So I'll give overview of basic LLM families, right? So when you look at encoder only LLMs, then examples are BERT, Roberta, Albert, DBERTA, XLNet, and so on, right? This has been trained using mainly book corpus, English Wikipedia, CC News, uh, storybooks, and so on and so forth, right? And ClueWave, Common Crawl, and so on, right? So depending on the number of tokens, you can see the quality also, right? Like say 137 billion tokens were seen by BERT model, which was the basic encoder only LLM, very good for retrieval and classification tasks. Then there was Roberta model, which has seen around 2.2 trillion tokens, unique tokens, right? From book corpus, English Wikipedia, CC News, stories, Reddit, and so on and so forth, right? Then there are Alberta, Deberta, and so on. Next, there are decoder-only models like GPT-1 and GPT-2. So GPT-1 was 120 million parameter model released in 2018, which has seen just book corpus. This was like one of the basic models which was released by OpenAI. Then GPT-2 was released with 1.5 billion parameter in 2019, which has seen Reddit corpus and so on. Then there was a whole bunch of GPT-2, 3, 4, 4.0 and so on. Olama, many other things were released, right? Then there are encoder decoder model. T5 is the most popular one, right? So T5 was a sequence to sequence encoder decoder model, which was pre-trained using common crawl corpus of 156 billion parameter size, right? Then there was MT5, the multilingual version of T5. Then BART model, which was released in 2019. Then another set of GPT family models like GPT-3, Cortex, GPT-4, and WebGPT. WebGPT was a very interesting model because it had models of the variant size like 760 million parameter, 13 billion parameter, 175 billion parameter, and so on. It was trained on Li5 dataset. Okay, then there was famous Llama family where the model parameters were released in public, right? Those were 7 billion, 13 billion, 33 billion, and 65 billion parameter models. Okay, then Palm family of models from Google was released, which was a very big, very large language model of 540 billion parameter size released in 2022 and so on. Okay, this is some sort of snapshot till 2023 of existing large language models of various sizes and the amount of data they have seen, right? Okay. Next, I want to show one trade-off, right? As you see, the number of parameter grows, like 1.3 billion parameter to 13 billion parameter to 175 billion parameter model, right? And the number of examples in context, like you give one example, no example, you give one in context example. Like in context example, I'll explain later in this talk itself. So think of it like giving one example for the model to understand, like who is the current president of US. Give it an example like Donald Trump, and then you ask who is the current president of India, right? So giving one example in the context is called in context example, right? Or is known as few shot inference of the large language model. As you see, when we give some examples, the larger parameter model performance improves. The smaller parameter model's performance also improves. You see that, right? The accuracy improves. Next is you see the performance of these large language models on standard, very complex exams, right? So these are exam result performances by the model. So you see GPT-4, the green one, right? The top dark green one. You see it has outperformed all other previous models, and it has got around 80% to even 90% in some of the exams like US ABO semi-final 2020. AP physics exam, you see it has achieved more than 70%, right? Score. And for SAT and GRE verbal, you see that, right? GPT-4 has achieved more than 90%. So it has like passed the exam with flying colors, right? So it is that good at reasoning and answering queries and questions of that level as well, right? Okay, so moving on, this is just a example snapshot of applications uses, right, and the quality of quality of the output produced by these large language models. Next, I want to present a timeline, a brief timeline including the Granite family of models. So GPT model GPT-1 was released in around June 2018, and GPT 1.5 billion parameter model was released in 2019, and so on. Every year, new GPT model is getting released, right? And as they increase the number of parameters, right, 175 billion parameter to uh, uh, further more parameters and so on, the performance improves, the reasoning capability improves, the capacity of the model increases, right? And the quality of the generations improves. It does not hallucinate much. It takes care of uh, biasness and all those negative things, right? uh, like it does not generate abusive content. It is very respectful in generating things. It handles hate, profanity, abuse very nicely, right? Then there was a Llama family of models, which was open source set of model. Even one model, Llama 3.1, has a variant of 4.5 billion parameter size as well, which was released in April 2024. Then Granite family of models were released starting from 2023, 2025, and so on, right? So 3.2 vision reasoning was released and so on. I'll show some performance comparison with standard models in the Granite family of model. Recently, we have released a Granite embedding R2 model, which is good at uh, doing retrieval. Like it can handle 8K context length tokens as well, right? And give you a good representation. It can be used for any classification task as well. Okay. So I want to show some, like, motivate the audience by showing what kind of examples or what is the capabilities LLMs have, right? What sort of capabilities LLMs have. So you can see basic LLMs have capability of world knowledge, like from Wikipedia. It can do Wikipedia QA. It can do multiple choice question answering, right? It can do comprehension, reading comprehension, summarization, simplification. It can do Boolean question answering, multiple choice question answering. It can do multilingual translation, cross-lingual question answering. It can do cross-lingual natural language inference, right? Entailment. It can also do coding tasks like function calling, API calling, and so on. And it has nice set of instruction following capabilities, turn-based, few shot, and it can do completion task as well, right? You say that complete this sentence or write this article professionally. It can do that and so on. It can do reasoning, it can do symbolic reasoning, arithmetic, numerical, logical, common sense reasoning. It can do. It has capability of in context learning. When you give some examples, when you give some steps, saying that this is an example of chain of thought, right? Or step by step solving this problem. Can you solve this problem similarly as the previous given example? It can do that. It can understand that. It can do symbolic referencing. It can interact with users, right? Assignment planning, virtual acting, physical acting. It can do all that. It can do role playing, right? It can say, assume you are this, you are a teacher, assume you are a professional mechanic or something like that. It can actually do that as well. It can do self refinement, self criticism. It can do tool utilization. It can tell you that, okay, for solving this particular task, you need to use this set of tools in this particular order and so on. Cool. It can do utilization of any database, any knowledge base, and so on, right? So all of these are like capabilities, or you can say applications of LLMs. Any questions, doubt till now, or am I going very fast, very slow? Yeah, anyone? Uh,
Pace is right. That's
okay, sure.
Yeah.
Okay, then I'll continue. Okay, so now coming back to the basic, like how this particular things are built, like how LLMs are built, right? Everyone has this question. Yeah, these applications are fine, this timeline is fine, these many models have come up, but how these are actually built now, right? So I have not gone into nitty gritty details, but I have tried to just uh, show some basic details, right? Like, so first you need data, of course. Without data, you can't train an LLM, right? So you need data. You need to clean the data. You need to tokenize the data using BPA encoding or word piece encoding or sentence piece encoding. Then you need to have a mechanism. You need to learn positional encodings, right? It is part of that transformer architecture. We'll go into details of positional encoding as well in the coming slides. Then you need to choose your LLM architecture, for which purpose you are trying to pre-train an LLM, right? Suppose you want to do retrieval, then you will go with encoder only model architecture. Suppose you want to train an LLM to do something, build a chatbot or generative AI, right? To make help of LLM for generations, like generation of text, generation of articles, and so on. Then you'll go with decoder only. Suppose you want to do it, you want to build an LLM for machine translation, then you can go with encoder, decoder, or any sequence to sequence architecture. Then your architecture is ready, your data is ready, then you need to pre-train the model. So for pre-training, you have multiple objectives like MLM, mass language modeling objective, CLM, causal language modeling objective, and next sentence prediction, like given the previous sentence, predict the next sentence, and mixture of expert objectives. So you need to decide based on applications which loss function you want to use. Generally, we use MLM for training encoder only models like BERT, robot, and so on. CLM for decoder only models. And we can use like next sentence prediction for sequence to sequence or encoder model. This is just like a sample. I have given example. So once you have pre-trained the language model, your model understand English text. It can do predictive generation. You give an input sequence, it will generate the output sequence, right? Or it will try to complete that sequence. But it has not been trained yet for your instructions, right? It does not understand what I should do when someone says, answer the following question based on the given passage. So you need to do supervised fine tuning using small amount of data for your particular task. Or you need to do general fine tuning or general instruction tuning so that it is robust to understanding user instructions, and it can do the tasks which user uh, gives in terms of prompt and so on, right? Then you need to do alignment. So you need to have a reward model to make sure that the output generated by the LLM is aligned with the human preference, right? Means that whenever LLM generates an output, it should be able to uh, change its output, tweak its output so that it is more like a human generated text, right? Otherwise, the generation would sound like it is not, it is hallucinated or it is wrong, factually wrong, and so on. So for that, you use GRPO algorithms, reinforcement learning algorithms with some human feedback, some specified heuristic rewards, and so on. Finally, once your LLM is ready, you are ready to prompt the LLM using your prompt instructions and your input. Then comes the decoding strategies. Do you want to decode using greedy search, beam search, or top K sampling with temperature, or top P sampling with temperature, and so on? Right. So, like you can start with greedy search, or you can start with beam search, anything. Like top K temperature sampling with temperature works really well. After that, once your training and decoding strategy, everything is set up, now you want to optimize its performance, right? Inference performance. So you can do that using KV caching. You can do that using quantization, bringing decreasing the size of the parameter, and so on and so forth. You can do knowledge distillation to bring the size of the parameter down, right? And so on. Okay. So this is the whole pipeline, sort of high level bird's eye view of training or building an LLMs. Okay. So now I'm going to start and talk about IBM Granite family of models. So we call it open, performant, and trusted uh, language models. Okay. So we provide language models. IBM provides language models for text, vision, speech, guardrail, time series data, embedding, accelerator, and geospatial data. Okay. So all the models, all the Granite family models are open, performant, and trusted. Open in the sense everything is so open source under Apache 2.0 license. Like these models can be freely customized, deployed, or used in commercial application everywhere, wherever you want, you can use it. There is no licensing issue. Performant, it has achieved very state of the art performance on when compared to standard GPT or other family of models, right? On a reasoning capability task, benchmarks, and so on and so forth. It is efficient, and it is cost effective and competitive. Then trusted. So IBM believes in trust, right? So all the data is has gone through a transparent process of cleaning, approval, legal approvals, security guardrails, and so on. And it has uncapped IP indemnification and so on. So it is trusted. Okay. Yeah. So open, like this is publicly available on Hugging Face, can be used by anyone. Use can be deployed using Olama, AWS, Red Hat, any platform you can use to deploy. And performance, you see the model transparency index, right? This is published by some foundation model transparency index publishing house, and you see IBM models rank fourth here. You see this with a score of 64, right? So our data is transparent, our model architecture, everything is transparent. We release a technical report with all the details. Going further, uh, like all that is fine, but are we training using good amount of data? Does it support multiple languages? Does it support programming languages? Does it support chain of thought reasonings? Does it has multi-model capabilities like video, speech, time series, and so on? Yes, it has all that. Now with the Granite 3.2 series, which can support around 120K token length as well, we are coming up with a new model which I'll present in the last slide. GPT-4 series of Granite 4 series of models, which will have unlimited context length support as well. Okay. So this is like how we collect the data, clean the data, and then do data deduplication, data annotation to reduce hate, abuse, profanity, right? And document quality checks. We do licensing detection and so on. Everything is done, and then after data filtering, we tokenize the data and then use this data in with approval from IBM's legal team to train the models. So the data or the model can be trusted. So this is just a screenshot from IBM Granite Hugging Face page. You can see we have released models, language models of size 7 billion, 3 billion, 9 billion, 8 billion, like all multiple parameter sizes with state of the art performance. for multiple tasks like vision, text, speech, and so on. Even for time series, speculators, geospatial, guardrail models, and everything. Okay, and we have also released smaller compressed version of the models. You can see IBM Granite 3.32B GGUF models, right? So these models are compressed small models which can be hosted on a low hardware resources as well. Okay, so this completes the first part of the talk. Now I'm going deeper into the architectures, the building blocks of transformers, the exact equations it has, and so on and so forth. Any questions till now? Or I can continue. Okay, I'll take it as no questions. Yeah, so I'll continue. Okay, so yeah.
Do you have any method by which you initially decide where from you should take this data? The source?
Okay, data sources. I will talk about that as well. The major source is web,
Where?
right? Yeah, web and Wikipedia book corpus, right? These are publicly available sources. And in the next slide, I will be like coming slides, I will be showing a data source called Blue Pile or Pile, which collects web data and all other data sources available publicly, which can be used for pre-training, fine-tuning, and so on. Okay.
Okay.
Yeah. Okay, so moving on, the building block of the so the basic of LLM is a transformer architecture, right? Everything is based on the transformer architecture. So what is inside the transformer architecture that we are going to look at now? So the first and most important component or building block in transformer architecture is self-attention block. So self-attention, as the word suggests, right? We want to attend to our neighbors, right? So this token can attend to all other tokens in the sequence. He can attend to all other tokens in the sequence and so on, right? Yeah. So it is like for generating the next token, where I need to focus on, where I need to attend to, right? So this self-attention, so transformer architecture is mainly based on two sub-module or sub-blocks or sub-components, self-attention block and the feed-forward net block. These are the two major blocks. People have tried with multiple variants of it, adding and removing things like layer normalization, residuals, and positional encodings, changing positional encodings, and so on. But like the core building blocks remains the same, which is the self-attention block and the feed-forward neural net block. Okay, so how we start? Given a sequence of tokens, or sequence of words from a vocabulary, right? Like say Juko made his uncle tea. Suppose this is a sequence of tokens, right? So for each word, we will attempt to represent that using a in an embedding space, right? So think of E as an embedding matrix of dimension vocab size cross. Suppose we want to take it to a space of 768 dimension, then the column size will be 768 and row size will be the vocabulary space. Suppose our model has a vocabulary size of 50,000 tokens. So we will have this embedding matrix of size 50,000 cross 768, right? So given an input token, we want to first project that using embedding matrix into a mathematical embedding space or a vector space. And given this vector space, we will further project it into something called as query key and values. So this Q, K, and V, capital Q, capital K, and capital V are learnable parameter weights of the transformer model. And we attempt to scale down our embedded vector representation of the token into a smaller dimension of queries, key, and value vectors. Okay. After that, after scaling down and introducing new set of parameters, we will calculate the pairwise similarity using dot product. So Q dot K will give you the pairwise similarity between the embedded and scaled representation of your input tokens. After that, we will try to assign like softmax sort of probability, right, with every similarity. So this eij, right? So the equation would be qi dot kj divided by root under dk for our normalization or decreasing the scale of the dot product, and then we will apply softmax to get the probability distribution. Okay, so then we will get a weighted sum of values, right? So in terms of oi, so for every value vector or for every token, I will get a weight. This weight represents the attention score. So for this particular token, how important is the all other tokens in the context, sort of. Okay. So yeah, so but after adding self attention also, we don't have a notion of order, right? Sequence. So we suppose there is a sentence, I went to the park. So whether I came before or went came before, right? So that order information is not available till now, right? Because we have not introduced anything to capture that order information. So for that, we have something called as positional encoding. Okay. So we will try to find out or embed the position like index one, index two, and so on, using a sinusoidal curve representation, which and get a vector representation of the positions. We will add this vector representation to our embedding vector representation xi. You remember from the previous slide, so that the embedded representation has the position information as well, right? Okay. So this is how it looks like. So position at index I could be like sine of I divided by 10,000 power 2 into 1 by d. Like this could be the equation, or this could be the mathematical formulation to get value of the positions and so on. Yeah. So the positive thing or pros about this is this has periodicity, right? You know, so you have seen sinusoidal curves or cos curves, right? It has a periodicity. It repeats after every time, right? That means it has absolute. It can capture absolute position embedding or representation. Yeah, and it can also extrapolate or maybe it can handle longer sequences as well, right? Because it has repetition capabilities. Yeah, the curve goes up, comes down, goes up, and again comes down, goes up, and so on. It repeats. But the only thing is it is not learnable, and even when the context length increases too much, like to say 5,000 tokens or 8k tokens or more than that, then this absolute position embedding doesn't work very well, and we have a lot of issues in handling that. Yeah, so the extrapolation thing that doesn't work really well there. So for that we have various other techniques like rotary position embedding, relative linear position embeddings, and so on and so forth. People have tried that to handle that. Okay, so but the net is modern modern architecture uses rope position embedding to handle longer sequence length tokens and so on, and the rope position embedding has the flexibility of extrapolation with which you can handle sequence as a relative position embedding of the tokens embedding, right? And then you can actually extrapolate this to handle 8k tokens or 16k or even 256k 128k as well. Okay, so this is how it is. Like suppose v and no has got a position embedding which is uh, 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 independent of its position. Like if no appears before or no appears after, it doesn't matter, right? Suppose I rotate no by two positions, like take it from here to this particular position, then we also rotate to this position, right? uh, then what happens is we can actually our embeddings will be invariant to absolute positions, right? Because inner product of the embeddings are invariant to arbitrary rotations, right? So I can have v here, and then in the next position I can have v know that, then this that could go on to the next rotation at position 0 as well, right? So basically my inner product becomes invariant of the arbitrary rotations. That way I can keep on handling longer sequences, and I don't have a position dependent embedding as such, strict absolute position dependent embedding. Okay, so this is an example of exact working of this position embedding and rotations in 2D matrix, 2D space, right? So enhanced transformer with rotary position embedding. Suppose this is the input sequence, and you see theta 1, theta 2, and so on is the position embeddings, and you can see after rotation with an M parameter, you see M parameter is trainable, right? Position M parameter. You can see I am able to capture information from my next set of tokens as well as and the previous set of tokens as well. I'm talking about the position encodings. Okay. So so we added position representation to the inputs to handle the order information. Now we don't have any non-linearity. Till now, all our parameters were linear parameter, right? Like the embedding matrix E, the Q vector, the Q matrix, the V matrix, and the capital K matrix. All were linear parameters. We don't have non-linearity here, right? So for deep learning, we need to have something non-linear, right? To learn the non-linear relationships. For that, we will add something called as feed forward neural net. Remember I told, right, two major components. First is the self attention block, second is the feed forward neural net. So what I'll do is I'll add one feed forward neural net consisting of ReLU non-linearity, and I'll add it over all the self attention layers, right? So now my network looks like this. Given an input token, it goes through a self attention layer followed by the feed forward neural net and so on. I have multiple layers stacked like this, and I'll take the final output representation from the last layer. Okay, so we added feed forward neural net, right, to each self attention output so that we add non-linearity, it can learn non-linear relationships. Okay. Okay, next is we need a mechanism to make sure that we don't look at the future, right? While predicting a next sequence of token, I don't look at the next tokens which will be predicted. Like suppose I have a sequence like I went to the park to play badminton or say to take a walk. So I should not see the past or the past future tokens while predicting a sequence, right? Like in machine translation or in language modeling. So for that, I need a mechanism to do that as well, right? So for that, I need a masking mechanism, right? So I need to mask out the future token. So you see here, while generating I should not, while generating start, I should not look at, while generating start, I should not look at the chef and who. While generating start and I should not look at chef and who. While generating start the chef, I should not look at who, right? So I should mask out this particular token. So we need to add masking to the attentions, right? So masking is basically setting attention weight of the future tokens to 0, right? While making the predictions. Okay, so this is how my whole transformer architecture look like. I have embeddings, text embeddings coming out using embedding matrix. I have positional embedding coming out of absolute position encoding or rotary position encoding or fixed position, flexible position encodings and so on. Then I have masked self attention because I added masking to the self attention layer, and then I have feed forward neural net. And finally, for projecting it to the vocabulary, I have a linear softmax layer, right? After getting the representation, I need to project it to the vocabulary space, right? These are the sequence of tokens I can predict. So for that, I have a softmax layer which will convert this logits into probabilities or vocabulary and say that, okay, this particular token has got the highest probability and this token should be predicted next. And these particular mass self-attention and feed forward blocks are repeated n times. Like you must have heard 10 layer transformer, 10 layer model, 20 layer model, 24 layer, 40 layer models and so on. So basically, as you go deeper, as you stack more and more blocks of mass self-attention and feed forward neural net, your parameter size increases, right? You have seen models of 3 billion parameter size, 7 billion, 9 billion, and so on. This is basically increasing this uh, encode this block multiple times. Okay. Cool. So we added self-attention, which is the basis or the basic method, basic of the representation. Then we added position representation, nonlinearity, and masking. Okay. So this is our this is how the transformer architecture and the model looks like. Okay. Okay, this is just details about multi-head. We can have multiple heads, and each head can perform attention independently, right? So we can, instead of having one particular head, we can have multiple heads, and each heads can look at different aspect, latent aspect of each token, and so on. Okay, moving on. This thing I already discussed, right? The self-attention part, Q dot K divided by root under D and doing softmax, calculating the attention in a multi-head attention set. Okay. Okay. Next thing is we want to optimize something, right? So this positional encoding and this particular attention block, right? Attention and feed forward neural net block has already been computed. So when we compute it for the next layer, I don't want to recompute this particular thing before moving into the next layer. So we have something called a residual connection, which connects the previous layer output representation to the next layer directly without going through this masked multi-head attention and feed forward neural net, right? So this is called a residual connections. And we also add normalization to control the precision values, right? Going up and down. Okay. So these are some of the optimization tricks. Okay, moving on. This is the final decoder only models architecture consisting of self-attention, add normalization block, feed forward block, and residual connections with a final linear softmax layer. Okay. Okay, moving on. This is the architecture of an encoder decoder architecture, encoder decoder LLM, right? Large language model. So like T5 and so on, where you have a encoder to encode the sequence and you have a decoder which can generate the sequence. The only change here is we have something called as cross attention layer here. Okay. So the representations of the encoder is cross attended by the decoder, right? So think of it like probability of modeling, generating the next token based on the representation coming out from an encoder. That's the only difference, and it has multiple transformer blocks. Okay. So transformer decoder is modified to perform cross attention to the output of the encoder. That's the only difference. And we have two transformers basically, one transformer to encode and another transformer to decode. You know. Okay. Okay. Moving on. These are some of the results. So you see for translation tasks on Blue Matrix for WMT 2014, 2014 benchmark, the performance was around 41.16 and so on for English French and 26.30 for English German. But using this particular mixture of expert model, we are getting similar performance with relatively lower training cost and so on. Okay. Okay. Yeah. So you see, sequence to sequence attention model was getting around 5.04 test perplexity. So the performance of a language model is evaluated based on perplexity, which is nothing but e power negative log likelihood, right? Something like that. Yeah. So the lower the perplexity is, the better the model is, the model's generation is. And you see, with the sequence to sequence attention model, the performance was, the test perplexity was 5.04 with a Russell score of 12.7. Russell is for n-gram recall. And you see the performance was just 12.7, but with transformer model with mixture of expert of dimension size 256, right? You see the performance has improved much, and perplexity is much lower, 1.90, and the Russell score is 38.8. Yeah. So transformer has outperformed all existing architectures like LSTM with attention, sequence to sequence with attention, and so on multiple important text generation tasks. Okay, so another benchmark called glue benchmark where transformer outperforms existing models and models and you can see T5 models get around 90.3, Deberta gets 90.8 and so on. So it almost get performance in terms of 90s. Okay, moving on. Any questions here before I jump into pre-training? Any questions on transformer architecture? Okay, I see some hands here. Kishore, can they ask questions or like, can you read the questions if they have?
So right now there is no question in the
No
chat
questions,
box,
sir.
sir.
We have questions through mail, sir.
Okay.
Can I paste? I can paste in chat box. You can see, sir.
Okay, yeah, you can do that. Yeah.
Yeah, just a minute, sir.
Or do we take questions at the end, very end? How
You
about
can
that?
answer
Because
this question now if you want, sir.
okay, sure. If it is related to transformer architecture, I can answer.
Uh,
How can we balance
after,
creativity with the ethical risk of defects and misinformation? Okay, okay, yeah. So I have not reached there, but yeah, the question is about risk of defects and misinformation. So yeah, like when data is synthetically generated, there are chances of model hallucinating, right? It is making up the stories, right? I have some examples in my slides where the model hallucinates. So that is a problem, and but people have used various reinforcement learning approaches to control the hallucinations, right? So there is a whole bunch of literature on hallucination mitigation. So to make sure that the model does not do does not generate hallucinated content, does not generate fake content, or does not uh, peddle some misinformation. Uh, that's why people have come up with grounded generations, right? RAG, where model has to give response grounded on some evidence, right? Model should give responses based on the references. Like I am giving this response based on this particular content. Okay, and there are techniques to optimize the quality of the generations, reducing the hallucinations and so on using RL. People have been exploring that. Okay, next question is you will use this in Olama, but there is no command available in Hugging Face to download the LLM, like pull Olama, put Llama to 7B. Oh, so these are like you can look at Olama documentation or to host the model or to serve the model and so on, right? So okay. Can you briefly explain about encoder, decoder, and encoder decoder models? I think I explained. So encoder models are for text representation and so on, and encoder models basically encodes the text and give you a compressed representation. You can add a classification layer on top of it to and fine tune it for classification task and so on. You can do embedding retrieval and so on. You can do many things using encoder only model. Decoder only models are actually trained for next sentence, next token prediction or the generative AI task, right? Like you say write an article about say Mahatma Gandhi, and it will keep on generating based on your instruction. And encoder decoder models are actually for sequence to sequence tasks like machine translation and so on. Now, decoder only models are in fashion and people are trying to use it for all the tasks, right? So, decoder only models for machine translation, for question answering, for text embedding as well. There are Qwen 3 embedding models which are based on decoder only models. Difference from encoder and decoder, both has same functionality. It's no, encoder only models cannot generate, right? It can give you representation. You can use it for classification tasks and so on, whereas decoder only models can give you a representation, can generate and so on and so forth, right? So that's the basic difference. What is the purpose of transformers in AI? Oh, So yeah, the transformers are the basic block for large language models, which are foundations for generative AI. The transformer architecture with self attention and feed forward neural net block is the building block, right? Is the architecture which everyone uses. They may modify it for their purpose and so on, but that's the basis for LLMs, and that's why it is really important. Okay, then I'll move on with the pre-training. Kishore.
So, sir, if you have any questions, I'll let you know, sir.
Yeah, sure. Okay. So in the next, I think 1 hour or 45 minutes, which we have, I will go over pre-training, fine-tuning, and how to do inference of the LLMs. Okay. So pre-training, right? So people started pre-training models, starting with Llms dataset, BERT, and so on. When BERT came, it outperformed all other existing models like LSTM, combination of LSTM, CNN, and so on by a large margin on text task. Right, that was the main motivation. So when people train like BERT using MLM objective, mass language modeling objective, where you mask 15% of the tokens in the input, and during training you try to recover those 15% tokens. They pre-trained using book corpus and Wikipedia and so on, and they observed that the performance on the downstream classification, sentiment analysis, all of the tasks improved by a lot. That was the main motivation. Then people thought that, hey, can I use it for text generation? Can I, because we have lot of text available, right? We don't need any supervision. We don't need human annotation. Lot of textual data is already available. I can just take that textual data and do self-supervised training. I don't need any supervision from human. Don't need any annotation and so on. So that with that motivation, people started pre-training models like GPT family of models started and so on and so forth. Okay. So people saw that data is available, self-supervised data is available in text, images, speech, structured format like knowledge bases and 3D signals. Can I train a foundation model which can, and then finally adopt it to question answering, sentiment analysis, image captioning, object recognition, image completion, image generation, image editing also nowadays, voice cloning, and so on. Lots of applications, lots of AI applications, right? So the basic is like pre-training the foundation model and then adapting to that particular things, right? Yeah, but the whole idea is pre-training has to be large scale pre-training, and it should see diverse data sets. You don't use label data during pre-training, and you can scale it based on compute you have. The more GPUs you have, the more layers of feed forward and self attention blocks you can have, right? More layers of transformer architecture you can have, and more number of parameters you can pre-train using large amount of data. Okay, cool. So for the first steps toward pre-training is, given a sentence, you have to map that to a vocabulary space, right? You have to create a fixed vocabulary of say 50,000 tokens or 125k tokens or 126k tokens, 128k tokens, right? You can't handle vocabulary of infinite size, right? You have to have a fixed vocabulary token, and you should be able to represent all the given large amount of text in that fixed, using that fixed amount of vocabulary, right? So, for example, common words, easiest could be like common words, hat, learn, these all things you can have mappings in the vocabulary like pizza, testy, and so on and so forth, right? For everything, you're going to have a mapping in the vocabulary, and the tokens like tasty and the spelling mistakes and so on, you can have a unique token, right? To represent that. But that also has a problem. I'll talk about that. So you see here, right? Tasty is there, but this tasty and the correct spelling of tasty is tasty. Right? That tasty means exactly the same. I cannot have different vocabulary mapping for both, right? So for that, general idea is that people use byte pair encoding. So you look at the most common adjacent characters like A and B are very common. Just add AV as a subword in the vocabulary. So you will not add words in the vocabulary, you will add subwords in the vocabulary based on the frequency of the character tokens, right? That is called as byte pair encoding. And you will create a vocabulary of like say 50,000, top 50,000 subwords. And that should be good enough to handle every token in your input, right? Okay, so your tasty will become like ta hash hash, which is a subword, a hash hash, which is subword, and sty, which is a subword, right? And learn will become lear and learn, and then this spelling mistake learn will be la hash hash and ern hash hash, right? So that you can have like a specific. You don't have to have vocabulary of infinite size. Okay. So common words end up being part of the subword vocabulary, and rare words are split into small components like TA and A and so on. Okay, cool. So the basic idea is uh, I shall know a word or I shall represent a word by the company it keeps, right? When I say I went to the bank to withdraw money, this bank means a financial bank. When I say I went to the bank to bring some water or to bring, say, lotus, this means a river bank. It cannot mean a financial bank, right? So we need to capture the semantics of the meaning, saying that this bank in this context means this, right? So that's the basic idea of representing text using the context. Okay. 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 I'll just skip. Yeah. Yeah. So basic idea is that how humans learn English, right? So I'm given a sentence like this. I put dash fork down on the table, right? So if I'm able to correctly predict a particular token for this, then I know English, right? I know understand. I understand the language, right? I can understand that this particular token should appear in this context, given this particular context, right? Left context and the right context. Okay. For example, this the woman walked across the street checking for traffic over underscore shoulder. If I'm able to predict this given the whole context which I have, then I understand the context, I understand the language very well, right? So that's the goal of pre-training using MLM objective. Okay, mass language model objective. Okay, I went to the ocean to see the fish, turtle, seals, and something, right? It can be sand, it can be water, right? Depending on the context, right? It cannot be like bank. Then the model has not trained anything, right? Learned anything from the pre-training corpus, right? Okay. So these are some of the examples, and you see, overall the value I got from the 2 hours watching it was the sum total of the popcorn and the drink. The movie was like looking at this, you can say, right, whether it is in the positive sense or the negative sense and so on, right? Yeah. Okay, Iroh went into the kitchen to make some tea. Standing next to Iroh, Zuko pondered his destiny. Zuko left the. Like looking at all the context, you can predict the next token, right? Yeah. Okay. I was thinking about the sequence that goes 1, 1, 2, 3, 5, 8, 13, 21. You can predict the next token, right? Yeah. If you have trained on a lot of these sequences, and generating these sequences is like a very easy task. Okay. So pre-training through language modeling goes like this. So you start with a sequence of token and you attempt to recover the next token at every time step. Like IRO, given IRO, predict goes, right? Given IRO goes, predict to. Given IRO goes to, predict make, and so on. So predictive decoding, right? You are attempting to predict the next token given the previous context and so on. Okay, so the model is like probability of predicting the next token given all the previous token which were predicted till time step t minus 1. Okay, okay, cool. So the pre-training task is to train a transformer like neural net architecture to perform language modeling given large amount of text, and then you save the parameter, network parameter. Okay, that's the pre-training task. Okay. Cool. So pre-training can improve the language modeling capability of the model, but it might not improve the task specific performance, right? It might not improve the capability of sentiment analysis. It might not improve the capability of machine translation. It has capability of generating the next token. That's the only thing, right? So for that, I can fine tune it on my task using instructions, right? So where I give some instruction like predict the sentiment given the context, and then I give the context, and then the model can say that okay, the sentiment is negative or sentiment is positive, and so on. Okay, this is just basics. You use stochastic gradient descent to pre-train and fine-tune the models. Okay, now moving on. Yeah, so I had a question about data set. So which data sets are used and how to get the data sets and so on. So there is a data set repository called Pile, which is composed of lot of data sets from variety of diverse domains, like PubMed, medical domain, law domain, archive of archive papers, Pile, common crawl. Then you have stack exchange of stack exchange questions of financial domains, economics, and so on. You have Wikipedia corpus, you have open web text, you have GitHub data, you have subtitles, lot of things, right? So the biggest chunk comes from this common crawl, which are web pages, which is around 9,000 GB, right? Yeah, and unique number of tokens are around 2,479 billions, these many tokens. And then we have Wikipedia book corpus, and then Project Gutenberg books, then semantic scholar papers, Reddit posts, GitHub code data, and so on. So this much amount of data, around 11,519 GB of data, can be consumed by a large language model using this next token prediction objective, and it can be pre-trained to learn the task of predicting the next token. Okay, around 3,000 billion tokens are available in 3,000 billion unique tokens are available in Pile dataset. Okay, this is one sample of pre-training data from DCLM. You see the text comes as a continuous sequence of tokens. Okay, artificial intelligence, a paragraph about artificial intelligence, hibernate interview questions, and so on. So book corpus looks like this. You have a lot of books like Walk in the Park, My Gift to You, and so on and so forth. And then you scrap these ebooks from the internet, right? Though it is controversial, like books have their copyrights and royalty and so on, all that is there. But if it is publicly available, people do that, and there has been issues in past, right? Like OpenAI got lawsuits and others for getting the data and so on. Okay, like you see, Google swallows 11,000 novels to improve AI conversation. Right? So that fair use is a concern. Anything available publicly on internet, people just crawl it and use it. But at IBM, we have a process of legal approvals and cleaning up and so on, and then before consuming it. But yeah, in general, existing LLMs just swallow the data which is publicly available and improve their performances. ChatGPT even uses your data which you generate during while interacting, right? So that it uses that data to improve itself. Okay, so I think I had a question about like what is the difference between encoders, encoder decoders, and decoders. So this is the difference, right? So encoders have bidirectional attention. It can look at the left context as well as the right context, right? So that's why it is trained using MLM objective, mass language modeling objective, because it can look at the left context as well as right context and predict the correct word or the correct token for the fill in the blanks or the dash, right? And yeah, so it is basically trained or pre-trained to build strong representation, strong embedded textual representations, right? Whereas sequence to sequence models has both encoder and decoders, where encoders is just used for representation and decoder decodes the information or predicts the sequence of tokens based on the representation given by the encoder. Whereas decoder only models, which are very famous and which can be used as encoders, encoder decoders as well, are trained based on language models, right? Based on language modeling objective called causal language modeling objective, which is predicting the next token given the previous set of tokens. Okay, I hope that clarifies. Okay, yeah, so I think I already told this that encoder language models can be trained using masked LM objective. So you mask some of the tokens and attempt to predict the value for those tokens. And you don't need any data for that, right? Because you can just take any sentence and just randomly mask 15% of the tokens and try to recover it. It's self-supervised. Like BERT model has been pre-trained using this. Okay. Yeah, this is one example. Okay, this is the architecture, or this is the you can say high level view of BERT model, which has positional embeddings, segment embeddings, and token embeddings, right? So given this sequence, like my dog is cute, he likes playing. So my dog is cute is one segment, and then he likes playing is another segment, right? And then you mask some of the tokens and attempt to recover that. Okay. Yeah. So BERT released two models, BERT base and BERT large. BERT base was around 110 million parameters size with 12 layers, 768 hidden dimension, 12 attention heads, and BERT large had 24 was 24 layer model with 1024 dimensional hidden states, 16 attention head, and 340 million parameter size. It was trained on book corpus, English Wikipedia, and it was pre-trained with 64 TPU chips for a total of 4 days. Okay. And yeah, now you can do it on GPUs as well using PyTorch and other lots of frameworks available. Yeah. So it is like
I think we lost him.
Yeah. Vishwaditya.
I don't know. After 1 hour, it goes off or what?
Oh, not the one.
No, sir, no, sir.
No, it won't go like that. We are have.
Okay. Okay. Maybe I'll
It won't
share
go.
again.
Yeah.
Yeah. Just give me a second. Yeah. Sorry for the inconvenience.
No, you beyond us.
Yeah. Okay. You can see my screen, right?
Yeah. Yes. Screen is on. Sure, is he still there? We lost.
He's there, but
No, no, he's there. He's fixing the issue.
Okay.
No, no, no. Oh, you can't see my screen?
It
Yes,
came
yes,
in
just
red.
now
Now
it's
it is come. Now it is come.
Okay. 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 Yeah. So I was on this particular slide explaining the performance. What is happening? I'm
then we
losing my
lost you,
screen.
sir. Then again we lost you, sir. Your
Okay.
screen has been lost.
Okay. I am sharing and then it. Okay. You can see my screen now?
Yes.
Yes.
Okay. Whenever this recording stops, my screen goes back. Okay. Yeah, some technical glitch maybe. Okay, so I was saying that pre-trained models, the performance was around 80 for natural language inferencing task, and you see the performance jump to 84, 86, and so on using BERT models.
Again, the screen went off.
Oh, what is happening here? Advanced sharing. Is someone trying to share or something? Share.
Oh, no, sir.
Nobody is trying to share.
Okay. Okay. Can you see my screen now?
Yes,
Again?
yes. Pre-trained encoder.
Okay. Sure. Okay. Okay. So these are okay. Okay. Some of the extensions of BERT were also proposed, like span BERT, which used to mask continuous set of tokens and so on. Okay, for multiple tasks and so on. Okay, I'll move on to this decoder only models directly, because encoder decoder models I can say currently out of fashion. Like T5 model was very famous, released as part of tensor to tensor paper, which got very good performance on multiple tasks like QA, sentiment analysis, translation, and so on. After that, decoder only models were able to outperform these encoder decoder models and even encoder models for multiple tasks. So the T5 model became out of fashion. So I'll just jump directly to the decoder only models. Okay. Yeah. So decoder only models attempt to predict the next token given the previous set of tokens. It has multiple transformer layers in it, and then finally linear softmax projected over the vocabulary, and then you back propagate through the whole network and update the parameters of the model. Okay. Okay, so I will explain about GPT, the first, I think, successful pre-trained decoder only model, which was around 117 million parameter size, and the number of layers were 12 layers. It uses byte pair encoding with 40,000 merges, and I think token size was also around, the vocabulary size was also around 40,000 tokens or so. It was trained on book corpus with over 7,000 unique books, right? And this was the first time the term generative pre-training was introduced, and the model name itself was kept as generative pre-trained transformer GPT. Okay, and this was fine-tuned for multiple tasks like natural language inferencing, right? Given a premise and the hypothesis, you have to predict whether this thing contradicts or entails, right? Suppose the premise is the man is in the doorway, hypothesis is the person is near the door. So does it entail or contradict each other? Right. Okay. So this is one task. So for that you can actually train the decoder only model or run inferencing like this. You can have the start token, then the premise, then a delimiter token, then you can have the hypothesis and attempt ask the decoder to generate the output like entailment, entailing, contradictory, neutral, and so on. Okay. You can add a linear classifier to project your representation down to a vocabulary or your dimension of your size, right? Like here there are three things, so I can project it to a three-dimensional space and then predict the label based on the output. Okay. So you see the difference gap, right? Previous models were getting like by LSTM with attention was getting 72.2 for this MNLI task. And the transformer, fine-tuned transformer was getting 82. Huge 10% boost in the performance. Okay. Okay. Then came GPT-2, which was able to understand the context given by the human. Like in a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researcher was the fact that unicorns spoke perfect English. So can GPT complete this? Can GPT generate next set of sentences given this human context or input, right? It was able to do that. Even a 1.5 billion parameter model was able to generate a continuous sequence of text which are grammatically correct. That was the motivation for GPT-2 for the pre-trained large language model, which was generating very convincing outputs. Okay, then GPT-3 came and whole story of generative AI changed, right? Because GPT-3 was very good at multiple tasks. It was able to understand instructions pretty well. It can be fine tuned, like it was able to do beat standard benchmarks by a huge margin. It had 175 billion parameters and so on and so forth. And this like pushed the development of large language models by a huge margin, and people started jumping into this and training their own large language models and so on. Okay. Okay, so yeah, then came the job of in context learning. Like if I give some input like 5 plus 8 is 13, 7 plus 2 is 9, and so on, given a new input, can the model generate output based on the pattern it has seen previously, right? And it was pretty good at it. It does a pretty good job there, right? That is called as in context learning. You give some samples in the example, and ask the model to predict output for your given input, right? Like like this is spelling correction, right? Given GAOT, you have to correct to goat. Given SAKNE, you have to correct it to snake. Given BRID, uh, c- c- change it to bird, and so on. So on these tasks also, it was like pretty good, right? And given this in context example, it was able to understand that and learn. Okay. And note that this does not require any gradient updates, parameter updates, and so on. It is just about giving some examples during inference in along with the input. That's it. Okay. Yeah. So you see the performance gap, right? You see for the sentiment analysis tasks, GPT-2 was getting around 45, 50-ish, but GPT-3 was getting around 55 and 60% macro F1, which is a very good number, right? Okay, so moving on, these are some of the scaling laws, like how much time does it take? How does the loss decreases as you keep on training, and so on and so forth. Okay, I'll skip this in the interest of time. Okay. Yeah, there is one more thing that Chinchilla was a model, I think, was a paper or the model which discussed about scaling laws. Like you have bigger models, you need more number of tokens, and so on. Right? Like you see here, GPT-3, the model parameter size was 175 billion parameter. The training tokens it has seen was 300 billion tokens. Whereas Chinchilla paper says that no. Even if you have a small parameter size model, if you saw more number of token, like 1.4 trillion token, uh, uh, it might perform better than the model which has 175 billion parameter model, right? So you see that 70 billion parameter model is better than much larger other parameter models. So this was presented in a study by Chinchilla. Okay. Okay, so these all things I think I have already discussed. Yeah. Okay, so this is about zero shot performance, right? Zero shot. A zero shot in the sense you don't give any example. You say that this is the passage, this is the question, and give me the answer, right? Yeah. So there is a challenge, or there is a benchmark called Vinograd schema challenge. On that also, large language models were performing very well without even giving any examples, like without even giving few short examples. Okay. Okay, this thing I have already explained. Okay, I'll just jump. Yeah, yeah. So this is a one few short example, zero shot, right? Translate English to French. You give English token, and it will generate to French. This is one shot, giving one example. Like she order is lottery ML in French for cheese. What is the French equivalent? It will give you that, right? This is one short example. So these are in context examples. Okay, this is few shot where you give multiple examples, right? And then you give the query or the input, and then it will output the translation for cheese in French. Okay. So yeah, next, this is very important. This everyone uses, like prompting, right? We prompt LLMs day and night, asking for our queries, uh, asking it to do mathematical computation, solving our problems, daily, day-to-day problems, and so on, right? So prompting, what is prompting? So prompting is like prompt is a text which, like humans, as we humans provide to the model for some conditional useful generations, right? And the process of finding this effective prompt for a task is called prompt engineering, and which is very important. You will see that in the coming talks as well. Some people will talk to you about prompt engineering strategies, and how do people do prompt engineering, how they improve the performance of the model by doing this simple prompt engineering, and so on. This is a simple example of prompt, right? A question: what is a transformer network? This is a prompt. It could be structured as well, right? You can say question is what is a transform network, and you have to predict answer after a colon. Okay, or it can be an instruction like translate the following sentence into Hindi, chop the garlic finely, right? So this is an instruction, and then followed by the input. This is a prompt. Okay, it could be a structure like, do you think the input has negative or positive sentiment, and you give the choices, right? And it could be like, assistant, I believe the best answer is, and then the model generates the next part. It could be like, you can give demonstrations of mathematical problem, let x is 1, what is x less than 3 in Python 3, something like that. Okay, what is the output of this? And then it will produce an output. I think these are the prompts which these prompts we use every day, like the programmers or the developers, students, engineering students use it like almost every day. Okay. Yeah, but the prompts can also act as a learning signal without even gradient optimize, based optimization or parameter update. The model can learn from the prompts or in context examples. Okay. And this is the new thing, like now models also require something called a system prompt. You can say, right, you are a helpful and knowledgeable assistant, answer concisely and correctly. You can be very detailed with the prompt, and it is supposed to follow your prompt and give the answer one. Like you can say that just answer directly, don't give any context, don't generate any other things, and so on. Hi, is there a question there?
No.
Okay. Okay, yeah, I'm rushing a bit because I have last 15 minutes with me, so I'll just try to complete few things which I want to cover. So yeah, this is about system prompt. You can give a system prompt, then user prompt will be like, what is the capital of France, and it will answer that correctly, concisely, and so on. So the current set of LLMs are very good at understanding instructions, and they are very good at following the instructions as well, and generating what is required. You can say that generate the output in JSON format. It will generate the output in JSON format as well. Okay, so prompts are not only very simple prompts. Like prompts could be like 1700 words as well. This is a prompt from Cloud Opus 4. You see that, right? Cloud should give concise response to very simple questions, but provide thorough response to complex and open-ended question, and so on. For more causal and so on, you can be very detailed about the prompt. Okay, cool. Yeah, this is one this is one thing, like you have this in prompt, right? So given this is the output, given this is the output, right? And given this, you say question mark, then this could not be the optimal prompt which you want to give, right? You need to give the prompt which is richer and which has things like multi-step reasoning to do this step by step and so on and so forth, right? So for the harder task, the prompt, the giving appropriate prompt is really important. Okay, you can give like chain of thought prompting, saying that suppose I have a standard, I'm using standard prompting. I said, this is the question: Roger has 5 tennis balls. He buys 2 more cans of tennis balls. He has 3 tennis balls. How many tennis balls does he have now? Right. The correct answer is 11. This is one example. And then I say that the cafeteria had 23 apples. They used 20 apples to make lunch and bought 6 more. How many apples do they have? The model might not answer it correctly because you have not asked the model to reason and understand, right? So there is, even though we have given in context example, we have not given the correct prompt here, right? The moment we say that uh, the moment we say that uh, there is a reasoning also involved, and we give that reasoning, right? We say that think step by step, and this is the reasoning. Roger started with 5 balls, 2 cans of three tennis balls, each in 6 balls, so total is 11. The answer is 11. So if we give this reasoning, the model understands and learns from in context reasoning and gives you the correct output along with the reasoning, right? So the prompting is really important. Correct and appropriate prompting is really important for getting the correct answers as output. Okay, and you see this, right? With chain of thought prompting, people are getting very good solve rate on GSM 8K. GSM 8K is a mathematical reasoning benchmark which has middle school math word problems. Okay. Okay. Yeah. So here we can also say, right, like, let's think step by step. We can add this token saying let's think step by step and then give the detailed description. Then the model will understand it better as well. Okay. You see that zero shot without giving chain of thoughts or explanation in the in context example, GSM Medk gets 10.4%. But when you give chain of thoughts in the examples, like zero shot example, right? Chain of thought, you say that let's think step by step. Then it gets around 40.7% on GSM 8K. The performance on multi-earth dataset also improves and it reaches 78.7%. Okay. Yeah, so this is the LM designed LM designed chain of thought. Let's work this out in a step-by-step way to be sure we have the right answer, and that gets accuracy of 82.0 on GSM 8K. Sorry, a multi-earth data set. Yeah, it was multi-earth data set. Whereas when you say like let's think step by step, then it gets around 78.7. Then you say first comma, then it gets 77.3. You see how a prompt is affecting the performance of the model on that particular task, right? When you say let's think about this logically, then it gets 74.5%. When you say let's think, then it gets around 57.5%. So this is just a study that giving correct set of prompt and chain of thought prompting is really important for solving mathematical reasoning tasks, right? Yeah. Yeah, so models are very sensitive to the prompts. Okay, I'll skip this. Yeah, so there's a Wikipedia page about prompt engineering, which is prompt engineering is a concept in AI, especially in NLP, and so on and so forth, right? So prompt engineering is appearing to be a new dark art. Okay, but there are some problems as well. Inefficiency, the prompt needs to be processed every time model makes a prediction, right? So prompt processing is another challenge, right? And fine tuning the model always outperforms prompting the model, right? When you fine tune a particular model on that particular task, it gets better performance than just prompting the model, the pre-trained model using that particular for that particular task. Yeah, so it is very sensitive. Your wording of the prompt is really important. Order of example matters. You change the order, you get better performance, right? And everything is hazy here. Like we don't know what model learns from the prompt, right? Even random levels might work. Okay, so now we'll see how models can be fine tuned on a particular task, right? On our particular task. So model can be fine tuned using full fine tuning strategy, right? You update all the parameters of the model, right? So if you update all the parameters of the model, you again need those many resources, huge amount of GPUs as you needed for GPU, as you needed for pre-training, right? So there is a strategy called parameter efficient fine tuning where you don't need those many GPUs and you don't need to update all the parameters. You can update just small number of parameters and get performance similar to the performance you would have gotten after doing full fine tuning. So that strategy is called PEFT, right? So there's a library on now there is a library on Hugging Face called PEFT library, which will convert, which will add very small, which will add a very small subset of small model parameters at every layer, and it will update only those small subset of parameters while fine tuning on that particular on any particular task using a supervised data set. Yeah, it gets around state of the art performance as compared to full fine tuning as well. Yeah. So yeah, because we need efficient strategy to fine tune because the pre-trained model does not understand pre-trained language model may not understand instruction clearly, may not be fine tuned on my client specific data or may not be fine tuned on my domain. So I need to fine tune it, but I can't spare those many GPUs for fine tuning as I spared for pre-training, and it is costly. So in order to avoid this hidden environmental cost of fine tuning, I can do some efficient adaptation. Like PEFT is one of the technique of efficient adaptation. Okay. Okay. Yeah, I'll just move on. Yeah, so there is another strategy called low rank decomposition or LoRa, using which you can actually do parameter efficient fine tuning of your model on that particular task. So you do SVD decomposition of a small set of parameters and you update only those parameters and then later merge with the model parameters, and then it is observed that it understands the task specific nitty-gritties and it performs very well on a particular task. Okay. So the common inductive bias on model parameter is sparsities, right? So the best thing is you can prune the models, right? So, but pruning also had its own problems. That's why you need to have a sub network, and you need to train that sub network and merge it back to the model weights. Okay. Okay. So I'll just move further to low rank decompositions. Yeah. So recently people have started fine tuning the models using low rank decompositions, right? So instead of fine tuning the whole 175 billion parameter of GPT-3, I can just fine tune a small set of parameters, right? So I can encode task specific parameter incrementally, right? So I have a smaller size set of parameter theta, which is much lesser than theta zero, and I'll just find out a gradient over theta, which becomes the gradient of theta, and then I can merge this theta back to theta zero, right? I'll find out that particular theta, that particular small set of parameter, which will give me better performance on for my this particular downstream task, right? So I'll maximize the log likelihood of p theta zero plus this small set of parameter of predicting the next token given the input and the previous set of tokens generated, right? So I just need to update this particular phi of theta, sorry, theta, not theta zero. Okay. So this is how it happens. I need to do introduce some new set of weights, so that when I add that weight along with some hyperparameter, I should be able to recover the original model some along with the new task which it has learned, right? So alpha is the trade-off between pre-trained knowledge and the task specific knowledge. Okay, and the only trainable parameters are this B and A. Okay, which is part of this new W. Okay, so people have observed that LoRa doing low rank adaptation of the model actually preserves the performance, and it gets performance better than or similar to the performance of a full fine-tuned model. Okay, this is simple implementation of LoRa. You introduce these A and B parameters, and then you initialize with Kemming uniform distribution. And this is your W is your parameter which you already had, right? Regular matrix multiplication. You just add that new introduced W and WV with your scaled alpha parameter. This is simple implementation of LoRa. Okay, and you see LoRa in practice, right? So for end-to-end analogy challenge, you see that, right? GPT-2 with full fine-tuning was getting around 68.2. With a low rank adapter, you see that it gets around 70.4. Better than that without even updating the full set of parameters, right? Yeah. Okay. So this is medium size GPT-2. This is large size. In large size also, you see it gets jumps, right? For in Blue Score, NIST, Meteor, and Roselle. So LoRa outperforms several baselines with comparable or fewer trainable parameters, with very less trainable parameters. Currently, people use LoRa, and there is quantized version of LoRa, QLoRa as well. Okay. Okay, so I'll just jump directly to QLoRa, where people further quantize the representations to 4-bit uh, and uh, uh, and improve the performance over LoRa, like the performance in terms of the number of parameters you need to update, So these LoRa and QLoRa fine tuning, you can do it on small single GPUs as well. You don't need huge amount of GPU resources as you need for fine tuning or pre-training, full fine tuning or the pre-training of the language model, right? Yeah. So they introduced something called as 4-bit normal float NF. Maybe this is the last time. Okay, something off. Yeah, you can see my screen, right, with from LoRa to QLoRa title.
Yes.
Okay, so I think yeah, I am almost done. Yeah, so I was here that you can move some of the parameters to CPUs, and you can do nice paging to optimize the GPU uses, and you can use small GPUs, small size GPUs even to fine tune on your particular task using QLoRa. Okay. Okay, all right. So other variants are like you can distill it to the smaller student model. So in our Granite embedding R2 model, we distilled a larger model to a smaller student model, right? Because deployment of this 175 billion parameter model is very, very costly. Per token cost is very huge, right? So that's why either you do QLoRa fine tuning or you can distill to a student model the knowledge, right? Okay, now coming back to ethical safety issues in LLMs, right? This point was raised, right? Misinformation, deepfakes, and so on and so forth. So, chatbots may hallucinate more often than many realize. So, be careful. You can't trust whatever ChatGPT says, it can't be correct. It might hallucinate. What can you do when AI lies about it, right? So, you need to have little protection recourse when the technology creates and spreads falsehood about them, right? Okay, I thought this question might come, so I have put this hallucination slide there. You see a news here. Air Canada loses court case after its chatbot hallucinated fake policies to customer. And the airline argued in the court that chatbot was liable. Airline is not liable, but court disagreed. So technology has to be used very carefully. You cannot 100% rely on technology always. You need to verify things on your own as well, right? Okay, privacy. So don't share, we should not share private data information with ChatGPT because it uses that to train its own model, right? To improve the performance of ChatGPT model. So somebody is saying how strangers got my email address from ChatGPT model because you might have given it knowingly or unknowingly. So be a little careful while using it. Don't share private data. Don't share your bank accounts, passwords, emails, private thing. Abuse and toxicity is also a problem, which was initially a problem. Now they're, I think, more or less sorted. So previously, when Google Bard was released, you remember, it had a lot of problems of abuse, toxicity, and hate. So that is another problem. So we need to be very much careful, right? Okay. Now, at the end, I think this is my second last slide. So we are going to release something called as Granite 4.0 or 4.0, which have lot of things. It has seen lot of data. It is the biggest model we'll be releasing. It is much faster, 2 to 5x faster. Has 80% reduction in memory requirement, 90% reduction in cost, and so on and so forth. It can even run on single GPU laptop on a single node and so on. Right. So release has been scheduled. Will be released soon. I think one tiny version is out there. So changes, we have added mixture of expert strategy for training. This is just a small modification, small set of new parameters added on top of transformer architecture. It has a hybrid design, linear scaling. It has no positional embedding, so it has unconstrained context length. Depending on your hardware support, you can have unconstrained context length. You can feed in the whole book also. It is efficiency focused, reduces memory uses and latency, and so on. That's all. Thank you. I think this is my last slide. Any questions so far?
Sir, we'll have the Slido quiz now.
Sorry, slide off.
Quiz competition. We'll have the quiz
Okay.
now.
Okay, sure. Okay, I'll stop sharing then.
Okay.
Okay.
Participants, I have pasted the Slido quiz link in the chat box. I request to join in the link. My screen is visible, madam.
Yes, Kishore.
Sure. Please join quickly. Let's see how quickly it can raise them. 16. 72. Why has he raised his hand? Prashu.
We'll wait for 2 more minutes to participants to join, madam. We have around 700 participants in live.
Wait for 500.
Yes, we'll wait till 500.
So probably we can invite the YouTube participants also to join this.
Let's see, 600. And how many in YouTube, Lavna? How many are there in YouTube?
Give me a second.
Once we reach 500, I will start.
Yes.
Participants, it's a timed quiz. We will have 20 seconds to answer a question. We'll have total of 10 questions. In each 5 questions, we'll have a leaderboard. Answering the question in 20 seconds in lowest time will be in the first place.
Minimum 300 participants are right now watching.
I think we'll wait for 600. No, but 800 are there. 800 plus 700,000 are there. So let's give them 2 more minutes.
Hey, have you posted the link in YouTube also?
See, the other way to do is log into www.slido.com and type in this number which is coming here. Join that quiz 1534255
You
259.
can also scan this QR.
Or you can scan the QR with your phone and then take it from there.
Once reaches 700, I will start.
Okay.
So the link has been already posted in the chat. YouTube.
Okay.
There was a population of 1,000, but then the YouTube can be multiple because it may be projected in a classroom and there may be many more people attending that.
Okay, the first question.
Let's start. Let's begin. 711. Read it out.
What is the primary training object used during the pre-training phase of modern decode only language models like GPT? We have 4 options.
First.
Okay, we got mixed response. A has 46% of the response. Okay, C is the right answer.
Caution.
Okay. Hope participants are used to do it. Only 20 seconds will be the timing. the next question. In the scaled dot product, attention mechanism, y is the attention score divided by TK. A 60% of the participants have answered C. Okay. Third question. Okay. 64 participants got the right answer. Percentage of the participants got the right answer. Fourth question. A 71% of answered B. Let's see. Okay, 71% of the participants got the right answer. After answering the fifth question, I request participants to come to the Zoom screen. We will display the leaderboard. After answering the fifth question, I request the participants to come to the leaderboard. So to the Zoom screen, we'll see the leaderboard. Okay, C is the right answer. Okay, I'm going to reveal the leaderboard. Okay. As of now, Harshini Angel is in the first place. She answered 5 questions in 37 seconds. Chandra Prasad in 45 seconds. Neeraj in 53 seconds. Vimal Anthony in 54 seconds. Padma Priya in 1 minute, 2 seconds. Now I request the participants to come to the Slido screen. We'll go for the sixth question.
Position including.
Okay. And the answer is C. Seventh question. This is the final question. I request the participants all to come to Zoom screen. We will see the leaderboard. Okay. Pranav got 10 answers correct in 2.2 minutes 15 seconds. Ria got 10 questions right in 2.25 seconds. Cherina got 2.30 seconds. Genia got in 2 minutes 37 seconds. Chandra Prasad got 9 questions in answer in 1.3 seconds. 1.23 seconds.
He was
Thank
only
you.
the one who was in the top 5.
Yes, yes.
See, all these people have overtaken the top 5.
Yes, madam.
Hmm.
Chandra Prasad who got 1 question wrong. So he became.
So he has come to the 10th position.
Okay. Now I request Miss Anuradha Ramanujam, PALS champion, to give vote of thanks.
Okay, thank you, Kishore, for that. And it is a wonderful session for paucity of time. I'll make my closing remarks short. I think it's a wonderful overall 30,000 feet overview for me for what is happening in this space of large language model. It will make a lot of sense if people observe life more, try to learn from their children how their learning patterns are. I find that it is very, very similar how you make the uh, machine learn something and what these large language models do actually. And it's all about predicting. It's like playing very close to the thought process of the other person. So we have to go beyond just thinking. We'll also have to think about how people think and how we can predict stuff comfortably. And that's what the language models are going to be doing for us, and all these whatever they call AI or uh, ChatGPT or Granite or whatever is going to help you with. When you say you're going to have, and it is going to be the future, you cannot say I'm more intelligent or less intelligent, but then we have to be intelligent enough to understand how this particular concept of AI itself works. And it was a great session to understand that and what is generative AI. I always misconstrued based on my English understanding of generative. It just means what is the next search, next possible word it would generate. That is generative AI. So that is a new takeaway for me from your presentation, Dr. Vishwajit. I would encourage all of you, all the present audience here, to go over and also go through this again and again. There were several papers, uh, research papers, information which was available, but it was skimmed through. So if there are faculty members also available in this group, you can try to help your students to read those papers if possible, and take additional thought-provoking discussions on whatever we spoke today, so that they will be more ready for the next session, which will come up on the 9th of September. So I thank all the 1,000 people uh, in the Zoom call, and another 300 who sat through the YouTube. YouTube is a lot more, though it says 300. Uh, they may be presented in a smart classroom where more number of people would be there. So we'll get the exact number as to how many actually attended from our PMO as we go along. And there is a feedback form, and we want you to go through that feedback form as well, isn't it, Kishore? We have a feedback form.
Yes, madam.
So we will share this with the speaker, and then we can make evolve a better session as well as we go along, because we also have to evolve as we go along and make it a better thing to be presented. Thank you so much for compressing so much of information into that, and that to a post-lunch session. It was highly challenging, and one thing is we don't get to see everybody's faces here, and I only hope people absorbed as much as possible from this session. There may be a lot of gaps. It's not possible for all of us to understand everything. So please go through a second time or a third time with the recording of uh, this projected in your classroom. Go through it as a group or with your faculty as well. get a grip of it. It's very, very important. We are presenting to you the latest and the greatest people in the system. IBM Research Labs, Dr. Vishwajit had found time to present it to you. Thank you so much, sir. And thank you to all the audience and all the PMO members who have made it happen. And my colleagues who are here, core champions who are here, Mr. Pati Lakshmi Narayanan, he's joining us from the States. And I think we had Krishna Kumar and the CEO Sujata were present. And many, many faculty whom I have been meeting recently are also there. Monisha and the SCSMV, VMV and RIT guys and KIT. So make sure you also put your, when we give you some instructions like prefix your college name there, it will be very, very useful for us to see who are the guys who actually were there on the leaderboard. Right now, I have no clue unless I go back and look at my registration list as to who all actually, which college these people are coming from. It's a free advertisement for your college, so please listen to every instruction that the PMO may give you. Please, next time you prefix the name of your college as well. Okay. Thank you, Dr. Vishwajit.
Thank you, ma'am.
Thank
Thank you.
you.
Thank you, everyone.
Yeah.
Thank you. No,
Thank you.
sir, this is Sujata here
Yes.
from the PALS Program Management Office. Thanks a lot for a wonderful session. Just wanted to add, if there are any questions offline, would it be okay if we share it with you and get it answered offline, sir?
Sure, sure. Please share it with me in an
Yeah.
Excel sheet. Maybe I'll answer.
Okay,
Sure,
I'll
thank you
share
so
it
much.
in my.
Kishore, can you please do that? From the next session, I think, we will ensure that the questions are first answered and then we will go for the other segments. I think there are a few questions that got added in the last minute, sir. But want of time, we are not be able to answer. But for the participants' sake, we will get all your questions answered for sure.
Sure, sure.
Also, the feedback remarks can be shared with sir so that he can.
Yeah, Kishore will mention that.
Sure.
Kishore,
Yeah.
you can take care of. Yeah, please.
Okay.
Thank you.
Thank you. Thank you,
Thank
ma'am.
you, sir.
Thank you, everyone. Thank you.
Sure. You want to wait?
Kishore, you have any instructions for the team, for those who are remaining? 3:30 are here.
Anu ma'am already mentioned about the next session.
Feedback, you're saying. It's okay, you can repeat it, Kishore.
Okay.
Keep it as part of your process, even if I say it by.
Okay. The next session will be on September 9th. On the same link, you can use the same Zoom meeting link to join the session. And also, the timing will be 1:30 to 3:30. Make sure you join with the next session. Thank you.
Thank you, Kishore. Hope all of you will fill up the feedback form which has been posted because it's one of the criteria for your participation. Close the thing.